In Chapter 9, we're going to be primarily balancing chemical equations. So if you go into the lecture and homework 11 folder and you scroll down here, I think this really summarizes, in fact, probably better than the PowerPoint, what we're going to do. This balancing chemical reactions hints. So when you're balancing chemical reactions, the most important thing is that you have the same number of atoms on each side. On the product side, you add up all the atoms, of oxygen, for example. And on the reactant side, that has to be the same number of atoms of oxygen, and all the different atoms. A big no-no is to never ever change the subscripts. The subscripts stay the same. What we're doing is we're going to put coefficients in front of the compounds. Here, let's show an example of that. So, here's an example where it's clearly not balanced. We have H2, or hydrogen gas, plus oxygen gas gives us water, H2O. And notice we don't have a balance, right? We have the hydrogen's balanced, but the oxygen's not. So we have to figure out how to balance it. All right, so we'll get back to that shortly. So what we're going to do is we'll put coefficients in front of the compounds. We'll start with the most complex compounds, and don't, if you happen to use fractions, that I really won't. I'll try to stay away from the fractions, but if you do use fractions, you have to multiply all the compounds so that the fractions are gone. The coefficients have to be whole numbers. All right. So and also this is just a nice little way to do it. So you start with the most complex compound. Leave molecules like oxygen or hydrogen. If they're off by themselves, leave that till the end. You'll see what I'm talking about as we do some of these examples. Also, polyatomic ions. Remember the polyatomic ions, if they're on both sides, and what I mean by that is they've survived. Let's say there's a nitrate on both sides. Then what you can use this substitution, or you just remember that it's nitrate, and you just use it you balance the polyatomic ion itself. Okay, so and some people like to use an X, for example, as a substitution, but then at the end you have to substitute back that it was nitrate that you were balancing. All right, and then you can also do an inventory on both sides of the equation and make sure that you have the same number of atoms. All right, so let's do one of these. This is pretty simple, but so on the left hand side of this equation right here, we have 2 hydrogens and 2 oxygens, and then on the right hand side there are there are 2 hydrogens and 1 oxygen. We've already talked about that. So if we put a 2 in front of the H2, then in front of the H2 and the H2O, you get this, right? So you put a 2 right here and then a 2 right here. So now, why is this balanced? Okay, so what you do with the coefficients, you multiply the coefficient times the subscript. So that gives us on the left hand side 4 hydrogens, right? 2 times 2 is 4. There's still 2 oxygens on the left hand side. Okay, so this is what's on the left hand side. We want the right hand side, the water, to be balanced. So 2 times 2 for the hydrogen gives us 4 hydrogen, right, which is looking pretty good. And then 2, remember there's a 1 that's implied as the subscript of the oxygen, so 2 times 1 gives us 2 oxygen. So both sides are now balanced, right? There's 4 hydrogens on this side, on the left hand side. There's 4 hydrogens on the right hand side. There's 2 oxygens on the left hand side, and of course because of this coefficient there are 2 oxygens now on the right hand side. So there's a nice little example. I don't know how much, the PowerPoint, they show some examples. You can go into it if you want to look at that. It goes into a lot of other things that we're just not going to cover. So remember, this is just an intro to chemical reactions. So here, I've got some here. I think it's just best to see these and to practice this. So I have the first reaction. This one right here is N2. This is supposed to be a 2. And I've written these out. N2, nitrogen gas plus hydrogen gas, gives us NH3. Okay, so just NH3, by the way, is ammonia. That's the common name for NH3. But what would this be? It would be nitrogen. So this would be, in this particular case, a covalent reaction. So it would be nitrogen trihydride is the technical name for that. And that's really nice for some of these. For example, like look at this number 2, right? It's going to be potassium chlorate, right? ClO3 is called chlorate. Goes to potassium chloride plus oxygen gas. So, and as you're going to see as you do the homework, and we'll do some examples like this too, that there sometimes it's nice to, or not nice, but people write out the words instead of giving the chemical formula. All right, so let's start this out. Here we have, this is obviously the most complex. The ammonia is the most complex molecule that we have. Now we have 2 nitrogens on, right here, and there's no other nitrogen anywhere to be seen, right? So the best thing to do is to put a 2. Remember, you always are dealing with coefficients. So the nitrogen is now balanced, right? There's 2 nitrogens on the left-hand side, which we started with, and now because of that coefficient, there are 2 nitrogens on the right-hand side. But now, how many hydrogens do we have? So it's 2 times 3. So that now on the right-hand side there are 6. But by the way, here's a quick way that you can do this, right? Since there's just 2 molecules, you can do nitrogen and hydrogen. So let's take a look. This is just a way of keeping track, okay? So let's see. And then nitrogen and hydrogen. That's supposed to be an H, sorry. So on the left-hand side we have 2 nitrogens, and now on the right-hand side there are 2 nitrogens. So we have to balance the hydrogens. Okay, so we have a hydrogen off by itself. There are 2 of them, as it indicates right here. But on the right-hand side, there's 2 times 3, right? So just to indicate that, 2 times 3, of course, so that's 6. And so to balance that on the left-hand side, I'm just going to put a 3 in front of that hydrogen. Okay, so that gives us 3 times 2, so that now it's balanced. Now this part down here you can use or not use. It's totally up to you. It's just a way of keeping track. When they're pretty simple like this, I tend to not do that myself, but you certainly can do it. All right, so let's work on the next one, I guess. I didn't leave myself much room. Hold on. All right, so let's do the next one. I just recopied this. All right, so we have potassium chlorate, right? ClO3, and this is a decomposition reaction. So notice the chlorate does not survive on both sides, right? So we're not balancing that as an individual polyatomic ion, that's a Cl, sorry, plus oxygen. All right, so there we go. All right, so let's start with the potassium chlorate over here on the left. That's obviously the most complicated thing. It has 3 atoms, right? So there's potassium, there's chlorine, and there's oxygen. And so the potassium and chlorine, as we can see on this side, are already balanced, because you have potassium chloride right here. The problem, of course, is the oxygen, right? And so we have 2 of them over here. There's 3 of them over here. An easy way to solve this problem would be, for example, to put a 2 right here, and then what you're going to have to do is you're going to have to put a 3 in front of the oxygen. All right, so now there's 2. There's 2 times 3 oxygens on the left-hand side, which is of course 6, and then 3 times 2, which is also 6. The only problem is now the potassium and the chlorine are not balanced, but of course that's pretty simple. If I just put a 2 right here, I've balanced the potassium and chlorine. And that's a balanced equation, right? You've got the same number of atoms of chlorine on both sides. You have the same number, I guess I should have started with potassium. You should have the same number of potassium, the same number of chlorine, and now the same number of oxygen. And that's literally how you do these. I mean, it's, you don't want to, don't be beating your head against the wall. Let's work on the next one. So we have sodium chloride. Sometimes I like to just name these things. Plus fluorine gas, F2, goes to sodium fluoride. So sodium fluoride plus chlorine gas. So I don't know if you remember this, but sodium chloride is salt. So you take fluorine gas, you add it to salt, you get sodium fluoride, and oops, I forgot the 2, right? There's 2. All right, so remember, in balancing these, we don't change the subscripts. And by the way, when you write this, I didn't do a very good job here, but you want to leave room to put your coefficients in. So sodium looks okay on both sides. There's 1 on each side. I'm starting with this molecule. It's not any more complicated than this molecule, but anyhow, the problem comes when I look at the fluorine. Okay, so I've got 2 fluorine on the left-hand side. So the only other place that you find fluorine, of course, is right here. So I've got to put a 2 right there. And of course, because I put a 2 right there, that tells me I've got to put a 2 right here. Why is that? Because the sodium is not balanced. But notice once I put a 2 there, then that not only does that give me 2 sodiums, it also gives me 2 chlorines, and I've already got 2 chlorines. So just those, a 2 and a 2. Okay, so I think we already had this one, but why not do it again? What the heck? Okay, so hydrogen gas, plus oxygen gas goes to water, H2O. All right, so really the only thing you can do is put a 2 right here, and that gives you 2 oxygen on both sides, and now that's 4 oxygens. 4 hydrogens on the right-hand side, so I've got to put a 2 right there. All right, let's see. All right, I'll balance this last one, or this next one. I mean, there's lots more to do, but look at what we have real quick. I only have 30 seconds. So this is lead 2 hydroxide. This is actually what we call an acid. This is hydrochloric acid. This is the stuff you find in the human stomach. But it would be hydrogen chloride goes to water plus lead 2 chloride. Okay, so we'll finish this in the next in the next video.